compositions, we have to find out what are the phases of the material system. Suppose it is one kind of alloy, that may be pure metal, or that may be alloy, or that may be a eutectic system. So for those things, we can find out the phases at various temperature as well as for various composition through this equilibrium diagram. So finding the phases for various temperature and composition is very, very important in the material science. To determine the various properties of the material, it is very necessary to find out the phases, because those phases will differ the microstructure, and as the microstructure of the system or alloy changes, then the properties of the material ultimately changes. So hence, to determine the phases present in the material system, equilibrium diagram or phase diagram needs to be plotted. So in that equilibrium diagram or phase diagram, on x-axis or on the axis, we are taking the percentage composition. So the composition of the material, different percentage of that alloy that we are taking, and on the ordinate or on the y-axis, we are taking the temperature. So there are various techniques or methods by which we can plot this phase diagram, such as thermal analysis, optical or electron microscopy, again X-ray diffraction, thermodynamic data analysis. But the most common method or mostly used method for drawing the phase diagram or equilibrium diagram is the plotting it by using the cooling curves. So in cooling curves, what are these cooling curves that already we have seen in detail. So by using these cooling curves, how to draw the equilibrium diagram that we have seen in the last lecture. So consider one example of copper and nickel alloy. So in copper and nickel alloy, the copper is taken at different percentage, and nickel is also taken at some different percentages. And see here, the copper is taken firstly for the first material in the 100%, and nickel is taken as 0%.
हॅलो सर,
Now,
आवाज खूप लहान येतोय तुमचा.
wait a minute. So am I audible now?
Yes sir.
Okay. So in equilibrium diagram, we have seen in last lecture how to plot that equilibrium diagram for copper and nickel alloy. We have considered one example, and that copper is taken for different percentages as well as nickel is taken for different percent in that alloy. And we have given names for that material. Suppose in material number 100% copper and 0% nickel is there. That means pure copper material for the material number 1 we have taken. Similarly, for material number 11, percentage of copper is 0 and percentage of nickel is 100%. Therefore, that 11 number material pure nickel. In between that 1 and 11 number material, so percentage of copper and nickel is varied. So for second number material, percentage of copper is 90, and sorry, percentage of copper is 90 and percentage of nickel is 10. For third number material, percentage of copper is 80, percentage of nickel is 20. So like that, we have varied the percentage of copper and nickel in different materials. And then that materials are allowed to cool at different temperatures with respect to time. And we have plotted the cooling curve first. So for material number one is a pure metal. So out of these two above diagrams of cooling curve, which I have shown here, which diagram is for pure metal? So the second diagram is for the pure metal. That means liquid plus solid phase is present in the BC line, on that BC line, which is at a constant temperature and having F is equal to 0. That means degrees of freedom equal to 0. So temperature as well as a concentration you cannot vary without changing the liquid and solid phase. That is the meaning of that horizontal line. So in that second diagram, it is a cooling curve for the pure metal, and the first diagram is for the cooling curve of the different solid solution alloys. For the alloys, the first diagram it is there. So in that chart, you can observe first and 11th. Those materials are for the pure metal, and other in between material from 2 to 10, all are for the alloys. So from that, we have plotted this uh, phase diagram so that percentage of that nickel inside the copper has been changed from L1. For L1 it is a pure metal, for L2 it is for the 90% copper and 10% nickel. For L3 that cooling curve is shown having the 80% of copper and 20% of nickel. Like that we have plotted all these cooling curve for the 11 materials, and L1, L2, L3, L4 up to L11 represents the liquid phases above which liquid phase will be there, and S1, S2, S3, S4 points will be there on that cooling curve are the solid points. That means below that points solid phase will be there, and in between those points L1 to S1, in between those points solid plus liquid phase will be there. So we have joined all the L1, L2, L3 points, and S1, S2, S3, S4 points. We have joined all these points, and we have got the two curves. First above curve joining L1, L2 up to L11 is called as a liquidus curve. That means the phase present over that line and above that line will be liquid phase. And we have joined the points S1, S2, S3, S4 up to S11. Those points are called as a solidus points, and we have joined all this point called that line we will call it as a solidus point, solidus line. And on that line and below that line phase of that alloy or pure metal will be solid, and in between these two lines, liquidus line and solidus line, the phase will be liquid plus solid. The phase will be liquid plus solid. Now this is a cooling curve for the alloy having the two metals, copper and nickel, which are completely soluble in each other, in liquid phase as well as in solid phase. At different temperatures, you can see also here in liquid phase as well as in solid phase, both are completely soluble. So this type of cooling curves we have drawn here. Now, for today's lecture, we will see second bit inside that, that is